A couple videos ago I mentioned Van Hoff factors. Here we're going to get into more of the details. Ionic compounds will produce multiple solute particles for each formula unit. And remember, colligative properties are just dependent on the number of solute particles. And so the theoretical Van Hoff factor, we use the letter I for that, is the ratio of moles of solute particles to moles of formula units dissolved. So you can just think about how many particles come from each formula unit and use that for your I. The measured Van Hoff factor is generally less than the theoretical because of ion pairing in solution. So the positive and negative charges are attracted to each other, and so your ions pair together. So when you measure your delta T for an ionic solution, it might be lower than you would expect. So here's ion pairing. You get the positive and negative charges interacting. And here are some of the expected versus measured Van Hoff factors. So you can see for sodium chloride, they're pretty close. But as you get more particles dissolved, you get lower than expected values. So let's work through an example. What is the measured Van Hoff factor if 0.050 molal calcium chloride has a freezing point of negative 0.27 degrees Celsius? So my delta T is going to be my molality times my Kf times my I, and in this case I'm going to be solving for I. So 0.27 is equal to my molality, 0.050 times my Kf. It's an aqueous solution, so that's going to be the 1.86, which you can look up in a table. You don't have to memorize that, times my I. So I can solve for my I, and I get an I value of 2.9 compared to the predicted 3. So it's slightly lower. Here's another practice. Calculate the freezing point of an aqueous 0.1 molal iron 3 chloride solution using a Van Hoff factor of 3.2. So my delta T again is my molality times my Kf times my I for a using the Van Hoff factor. So my delta T is going to be 0.10 times the 1.86. Again, you don't have to memorize that, times 3.2. So my change in freezing point is 0.595 degrees Celsius. So my freezing point is actually negative 0.60 degrees Celsius. More practice. Calculate the theoretical boiling point of a solution made by dissolving 10 grams of sodium chloride in 54 grams of water. So we know that my delta T is going to be my molality times my Kb in this case times my I. My Kb for water I can look up is 0.512 degrees C per molality. And my molality, remember, is moles, in this case of NaCl, per kilogram of water. So my moles, 10.0 grams times 1 mole of sodium chloride is 58.44 grams, which gets me 0.171 moles of sodium chloride. And then I have 54 grams of water, so if my molality is going to be that 0.171 moles divided by 0.054 kilograms of water, which is 3.17 mole. So my change in boiling point is 3.17 times 0.512 times 2 for my Van Hoff factor for sodium chloride. So my change in boiling point is 3.24 degrees Celsius. So my new boiling point, remember boiling point is elevated. The normal boiling point of water is 100. So my new boiling point is going to be 103.2 degrees Celsius. We've spent this chapter talking about solutions, but there are other mixtures that are not homogeneous. So solutions are defined as a homogeneous mixture. A suspension is something that is heterogeneous, and as you let it stand, it separates into two phases. So an example there would be something like salad dressing, that's oil and vinegar, that when you shake it up, it seems to be one phase, but as you let it sit, it separates. And then colloids are also heterogeneous, but they do not separate on standing. So an example there is milk, where you have fat particles suspended in a solution, in the liquid phase, but it doesn't separate on standing. It also doesn't separate through a semi-permeable membrane. Parts of it would be left behind. So here is different examples of mixtures, comparing solutions to colloids to suspensions. One other thing I want to mention here is the Tyndall effect, light scattering. And so solutions don't scatter light. Colloids, you get this Tyndall effect, which we'll talk about on the next page, and then suspensions scatter all light. So if we look at colloids, the Tyndall effect, you get this bending of light. So examples like fog, you know how light looks in fog, you get the Tyndall effect, where you get the light scattering. You can get solid aerosols, solid dispersed in gases, so smoke is an example. Foam, you can get gas suspended in liquids. Milk is an emulsion colloid, where you have fat globules in water.